I don't know how many of you read the citation for the prize. There were three main topics. There was spin classes, which Rav will talk about. There was chaining, which Michel and Sarah talked about. And my main goal here is to discuss the remaining two, which the main one is concentration of measure and also Maharam's problem. But what I want to do is to try to indicate how much these ideas go far from probability and how much work there is of Michel, which is very different from these topics as well. So it's really all around mathematics, and the ideas are, it's not just statements of theorems, but it's insights that are being used in many places. One thing that I want to say that this is Sarah, when we split it up in a way that I didn't get to talk about chaining, this is the hardest thing for me, to force myself not to talk about chaining. So chaining appears in many, many, many places in a very, very, very powerful way, and this is the one thing that I will not cover because it was covered before, even though it should be covered. Okay, so I want to start with Maharam's problem because it's chronologically where Michel started, but also because I think that most of the talk will be in concentration of measure and we can easily just get trapped there. So I want to get one thing which is a little different. So the situation is the setting is very simple. You have some set. People are far away. Is this big enough? Yeah? You have a set, and let's say sigma is an algebra of subsets of X. So I wrote sigma because I'm used to sigma algebras, but this is just an algebra, so it's a collection of sets which is closed under intersection, union, contains the empty set. And complements. Okay, and so now you have a function that assigns to every set some non-negative number. Right, so f of a is some number non-negative, and a for every a in sigma. And we'll say that it's a submeasure if very obvious axiom. So we say that the empty set is mapped to 0. It's monotone, so if A is a subset of B, then f of A is less than f of B. And it's subadditive, so f of A union B is less than f of A plus f of B. Okay, so it's, and then it's a measure if there is equality. So this only in this, very soon I'm going to pass to sigma additive measures, so, but just in this part, I'm going to say measure, but I'm going to mean finitely additive. So if there is equality, when A and B are disjoint, so if there is equality, then we say that it's a measure, but it's finitely additive. Okay, so this is the setting. Now we're interested in functions which have the following property, which is called exhaustive. So suppose the following holds. So whenever you have a sequence AI, these are elements in the algebra, and they are disjoint. So for every disjoint sequence, so no two of them intersect, whenever that happens, the limit of f of AI is 0. Okay, so that's what's called exhaustive. I'll get to this a bit later. Suppose this holds. So but there is a quantifier for every choice of sequences of set that go to 0. So does anybody see in their mind an example of a function that has this property? Whenever you have a measure, it has to have this property, because f of a sum, or f of the union of a1, a2 up to an is equal to the sum of the f's of ai, which is at most f of the entire space, which is some finite number. Okay, so this obviously holds. If f is a measure, but it also holds if a little bit more. It holds if also holds for the same reason. If f is absolutely continuous. With respect, let's say, to a measure mu, by that I mean, give me an epsilon. For every epsilon, there is a delta, such that if you give me a set where mu of A is less than delta, that forces f of A to be less than epsilon. Or if you have a sequence, the same thing is saying if mu of ai tends to 0, then also f of ai tends to 0. So that's by design holding whenever f is absolutely continuous with respect to a measure. And Maharam in the 40s, Dorothy Maharam, so it's the 1940s, I don't know exactly when, conjectured that this is if and only if. Okay, so that if you have this astringent property, so for every choice of disjoint sets, f tends to 0 along them, then this can only come if f is controlled by, is absolutely continuous with respect to a measure for which this is obvious. Okay, so so that would be a very nice result. This was a truly central question in measure theory, a very, very old and central, and many people looked at it. Many equivalent formulations, many applications. It's quite close to being true. So in 1979, Michel conjectured or suggested the following stronger version. So let's look at this conjecture. In this condition here, there is just a limit. We're not saying anything about rates. So let's introduce some rate. Let's make this uniform. So this is just terminology. F is uniformly exhaustive if, again, for every epsilon, there exists an n such that if A1, AN, elements of our algebra are disjoint, then one of them, so the minimum of f of ai is less than epsilon. That's a stronger version. There is right. There is you want it to be small. It's enough not to, you're not looking at the infinite sequence. Just there is some n depending on epsilon. Then one of them will be less than that. And that's again obviously true for a measure or anything which is absolutely continuous with respect to a measure. Right. For a measure, it's right. The n will be linear in epsilon, in 1 over epsilon, because the sum of ai will be less than mu of x over epsilon, so one of them is less than epsilon over n. And Michel conjectured that, well, this is a special case of Maharam, but at least in this case, it's true, and this is a wonderful theorem. So this is truly, I highly recommend reading this paper of Carlton and Roberts. In 1983, this was a 79, where he studied this question, and he proved that it's true. So if F is uniformly exhaustive, then it is absolutely continuous with respect to a measure. So that's a great positive result. It's a superb theorem. The proof uses expander graphs, even though this seems like this has nothing to do with combinatorics. And I think expander graphs have been immensely powerful in computer science, for example. But I think if this is not the first really serious application of expander graphs, it's one of the very first. And it was done by analysts. So the proof is interesting, and it brings in concepts that were afterwards really revolutionary in mathematics. The reason, Michel, I think you made this conjecture is because your paper and earlier papers of Christensen, etc., we were trying to build a counterexample to Maharam's problem, and those attempts failed. And you saw that this lack of uniformity is what's going on. So, no, sorry, you were in all the attempts. There was this uniformity, and that's why the attempts failed. So it was a natural thing to make this conjecture. It's interesting. So, as I said, this was one of the first really substantial uses of expanders for a serious application. But very recently, I think in 2016, the proof in this Carlton and Roberts has also had decisive applications again in computer science. So there is very recent developments which actually use that theorem to solve questions in computer science. So that was, I think this is where it was left off. Until I'll do my best to write in a stronger way above the bad erasing. Until Talagrand. It appeared in 2008. I probably was a preprint for a while. Proved that Maharam's conjecture is false. Okay, so, and this is not just a construction of a counterexample. Let's think for a moment what has to be done. You have to cook up a set with an algebra of subsets, a subadditive, a submeasure on it, which satisfies this condition. So you have to be able to prove that it holds for every sequence of disjoint subsets of the algebra. So there is something interesting just even checking that it satisfies the condition. And then you have to prove a theorem which has a quantifier every measure. No measure controls. For no measure, your F is absolutely continuous with respect to it. So it's a counterexample which has, but you have to prove a theorem with every measure in order to do that. So this is, thank you. So this is, I think, a beautiful story. I think this was related to your dissertation problem, right? Did the Shouquet suggest it to you, the Maharam problem, or? I don't. Yes? You don't, okay. But in any case, Michel returned to this so many years after and just obliterated it. But both the positive results started from a question that he asked, and it led to very nice mathematics, and the proof that it's false is a very interesting proof. So this is an early chapter of Michel's contributions, but whose closure actually is recent. So now my talk is eclectic because I want to show many things. Now I want to pass to a concentration of measure. Okay, so concentration of measure. And this is a property of a probability space. So you have some omega p, a probability space. And we want to say something along the lines of every large subset of this space, so you choose your favorite large subset of your set omega. So for every large subset, so it's something of the form, we want to say, for every large subset A of omega, almost the majority or most of the points of omega is close to A. And something which is essentially equivalent, which is for every nice, say sufficiently continuous function f on omega, f is almost constant on most of the space. Okay, so for this to make sense, so these types of phenomena are known to be equivalent to each other under reasonable conditions. This is the same thing. This is a property of the space. It is vague because there are all kinds of things that we didn't say. So large, okay, it's a probability space. So let's say probability at least a half. So also most could be interpreted in this way. This is problematic, close to, because we're not dealing with a metric here, or there's no notion of closeness. And the analogous thing for functions would be, what do we mean by continuous? Okay, so we have to, what does sufficiently continuous, or what does nice function mean? And so I'll give you examples, and then I'm going to state and explain a proof of one theorem of Michel. But a hallmark of Michel's transformation of this area is that he invented highly original interpretations of what's underlined here. So he discovered phenomena which would not be your first guess, and then introduce additional structure which is hidden in the problem. So the first guess would be, don't just take a measure space, a probability space, but also put some metric on it. And close means close in the sense of metric. And let's say sufficiently continuous would be Lipschitz function or something of this type. And that was essentially the entire. There's a very, very nice work earlier in this and very influential work But everything was kind of in this vanilla setting until Michel came along. So before I state something, let's just analyze. Let me tell you some examples. So the kind of thing that you should imagine, this sounds strange, but it's, so take omega to be, let's say, the Euclidean sphere. So this is just all the points. And then P is just going to be the surface area measure. On the sphere, normalized, so it's a probability measure, okay? And then, so for example, here's a nice example of a function, f of x, 1 up to xn, is x1, the first coordinate. Okay, so this is just a computation. You can see that, you can check that for every epsilon bigger than 0, the probability that this f, is bigger than epsilon is less than e to the minus c n epsilon squared. When I write twiddle, I mean a universal constant, 2, something like that, or some universal constant, and also when I write c, I mean universal constant. But you see, if you ask where is f bigger than 0.0001, if this is the epsilon, this happens on the sphere. Of course it happens on the sphere. x1 can be as large as 1. But it happens on an exponentially small fraction of the space. And this is just a computation. Okay, there is nothing, this is a specific f. The phenomenon, the reason the sphere satisfies the concentration of measure phenomenon is that this holds for every one Lipschitz function f. So Levy proved in the 20s, or I think 20s, that this holds for every, let's say, one Lipschitz function f. Okay, or equivalently, every subset of the sphere which has, let's say, at least half of the mass, right, so you take some, this is the sphere, take some subset, A, which has at least a half of the mass, and now you look at its epsilon neighborhood, so you look at all the points, so A epsilon is all the points in the sphere whose distance from A is less than epsilon. Let's say the Euclidean distance or the geodesic distance on the sphere. This set, P of A epsilon, is at least, or maybe the complement, okay, is at least 1 minus c e to the minus c n epsilon squared. It's the same thing. You can pass from one to the other. So we computed this for special f, but it's actually the reason the phenomenon holds here is that it holds for every reasonable f. And that is an immensely powerful thing to know when you have this. So, so I think it's fair to say that before Michel came on the scene, there were two types of ways concentration of measure phenomena theorems were proved. One of them was a kind of maybe a variational argument, which is just solve this optimization problem. Look at among all A's with, let's say, measure at least a half, find the one which minimizes what's written here. And you can do local perturbations, local symmetrizations. There are ways to, and there are also some, there are other ways, but it was solving this problem exactly, understanding how to solve this problem exactly. That's one of them. And the other one was this intuition, which is a correct intuition, which is when your measure space here there is something very high dimensional happening. There's input from many random variables that are somehow uncorrelated with each other. let's say, independent. They don't have to be independent. But each one doesn't contribute much to the value of f. When that happens, you have a phenomenon of this type. And the proofs really just examined that directly. So martingale, the compositions, you just understood what is the contribution of each of these hidden variables or underlying variables. You wrote it, the value of f is a sum of these contributions, and you prove that all of them are small. There are ways to encode these. There are spectral methods. There's Poincaré inequalities. But morally, it's always writing the value of f as a sum of small contributions and showing that the increments don't contribute much. So this changed completely by works of Michel, and so there is a mini monograph that he wrote, but there were also earlier papers of his and later papers that led to it and came from it about concentration of measure. I'm going to explain one theorem, and I'm going to want to indicate his proof, because this is a method that people call a Talagrand induction, so I want to explain what a Talagrand induction is. But before explaining it, I want to give you an example of what it's good for. So for example, let's just so I'll write down the inequality in a second, but so there are two types of applications of concentration of measure, of your work on concentration of measure. Most of them are saying that certain very interesting, specific random variables are concentrated. Okay, I will example, traveling salesman problem, bin packing, etc. They're very, very complicated. They're definitely not just the first coordinate, and yet you can prove deviation inequalities of this type. So there's a whole list, and people definitely care about concentration inequalities. But what's intriguing is that there are many theorems which have nothing to do with probability in their statement, and we only know how to prove using, let's say, the inequality, Talagrand inequality that I'm going to write next. So here I'm choosing one. I'm not saying it's the best one, but it's the one that I think anybody can understand. And it's the following thing. So here's a fact, an extremal fact in graph theory that has nothing to do with probability. And the only way we know the answer that I'm going to show you is through Talagrand's inequality. So you have a graph. So G is let's say, it's a combinatorial graph. Say on n vertices. So this is just, you have n points. And some of them are joined by edges. As simple an object as you can imagine. And you ask them, so whenever you have, this is something which is standard in mathematics, you look at, it's very natural to ask, and this has decades, what I'm going to say now is something that has been studied for decades, is how large do universal objects have to be? So the question is, how large should n be so that G contains all k vertex graphs. Okay, so let's say k equals 6, so you can try to do it. It's something that anybody can try to do on a piece of paper. You can write down all the graphs of size 6. Let's say 5. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, I don't know how to count. So here is 1, and here is, suppose I'm going to, maybe here's another or another. You can write down all the 6-point graphs, and you want all those pictures to appear in the n-vertex graph. So let's say you want, so for this one, you want that somewhere in this universal object, there will be 6 vertices which have this appearing, and on these 6 vertices, this is exactly, that's what's called an induced subgraph. So whenever you have some mathematical object, it's very natural to ask how large or how small or how large should a universal object be, okay? And the answer is, we know it today, but it's only in 2017, it's a theorem of Alon. This is a theorem, Alon, from 2017, which says the smallest n, such that you can get an n-vertex graph, which contains all k vertices, all k vertex graphs, is up to a little of 1. So with up to an additive lower order term, it's 2 to the k minus 1 over 2. Okay, so for example, okay, there's a little of 1, but let's say if k is 200, then we know that the answer is roughly 2 to the 199. Okay, but there's a 1 plus little of 1, so as the 200 goes to infinity. Okay, so this is a basic question. There is a long history of this from the 60s. The solution uses, deep in the proof, the exact Talagrand inequality, which I'm going to now explain, and we do not know how to do it otherwise. So but this theorem has nothing to do with probability, and there are many things of this type that these things are useful for. So let me tell you what went in the guts of the proof of that. And this is the following beautiful approach. It's extremely creative. As I was looking up papers that refer to that paper, I found all kinds, and I won't name names, but there were multiple authors. When they introduced your inequality, they described it, they said, we're going to use the following unusual inequality of Talagrand. And many people use the word unusual. So it is genuinely a different perspective than what was done before. The creativity here will be both in the formulation and in the proof that I'm going to indicate. So here's the setting. So suppose you have n probability spaces. So let's say mu1, omega 1, mu1 up to omega n, un are probability spaces. And omega is just going to be the product. And then u is going to be mu1, the product. So, right, so the points here are n tuples of points. So you select the omega 1 independently according to mu1, omega 2 independently according to mu2. It's up to omega n chosen according to mu n, and they're independent. And this is the probability space. You see high dimensions appearing here. Obviously, there is a product of many sets. Okay, so, and then you do, so this is the theorem I'm going to say is going to be in this setting, and this should already be concerning because I opened by saying we need some metric, some notion of what it means to be near a set. There is no such thing. So the creativity comes here by introducing something external to the problem. A notion of distance, which isn't written. This is just in the context of metrics, of measure spaces. There is no metric yet. So what Talagrand did was the following. So you take a set A, a subset A of this big product space. And by the way, you can think, and in most cases, this is good enough for the applications. You can think of omega, and later maybe I will. It's just the discrete cube, so just the vertices of the n-dimensional cube. is 2 to the n points. What I'm going to say is new in this case. New. It was new in the early 90s. So you take a set A and the point X. And I want to say, what do I mean by X is nearby A? There was no distance. So I artificially, Michel introduces something to the picture, and it's the following. You associate to this pair a set U XA. It's going to be a subset of the cube. So it's just defined as the following. So you run over all the points y in A. For every such y, you write the following vector. You write a vector of 0 and 1, so it's a subset of 0, 1 to the n. I'm going to write 1 in the ith coordinate. So if xi is not yi, and 0 if xi is yi. So I'm just encoding, and I'm running over all the sets A. So this is a big product space. I have a subset, which is some bubble in it, which contains half of the points in the product measure. And for every point, I run over all the points y in A, and I just look at the indicator of where y is different from x, the coordinates where y is different from x. Is that clear? So this is a subset over n of the cube here. So let's say these were, I want to be able to draw what I'm about to draw. Okay. Let's say these 3 points, but it's higher dimensional, okay? And now, the notion of closest of x to A is phi of xa that Michel defines, and this is really out of the blue at the time, is just the distance in the Euclidean metric between 0 and the convex hull of U x A. So that, I mean, it's the minimum of the Euclidean length of a point z. Z is in the convex hull. Right, so in this low-dimensional picture here, if that was A, then I'm going to look at this. The convex hull is going to be this triangle going from this edge to that corner. Here is 0. And I look at what is the nearest point. Okay, so if x itself were in A, then this would be 0. Because one of the points would be, right, if y is x, then you have no 1s here. Okay, so 0 is already in the set. Does everybody see that? So this is some funny notion of closeness of a point in an abstract set, an abstract product of spaces, to a set by introducing Euclidean structure and convexity to a problem where it wasn't written before. Okay? And the theorem (1992, 3, something like that, up to the exact theorem. The theorem is that if mu of A is at least a half, then mu of the set of points where phi xa is bigger than epsilon, is less than e to the minus c epsilon squared. Independent, there's no n appearing here, even though this is a product of many spaces. This is very important. So this notion of closeness, this happens rarely, but there is no dimension in the picture. And I hope you realize that there is something creative here. This is introducing into the picture a structure which wasn't in the original setting. Okay. So, okay, so using this, there is a slew of results that you can. This is an extremely useful fact. This appeared in the theorem of alone that I showed you. There are all kinds of random variables that this shows that it gives the best known concentration inequalities for. I would not be surprised if once a week there's a paper that appears that uses this and solves some problem. This is an extremely useful fact. Like, for example, so you can do, let's say, TSP, the traveling salesperson problem. Right, you can imagine, so you have endpoints, x1, x2, up to xn. Let's say they're all in the unit square. And the traveling salesman, TSP of these points, is the shortest path that goes through all of them. Okay, I hope that you have seen this is a very classical optimization problem. It depends in a very complicated way on the inputs, x1 up to xn. But so if x1 up to xn are IID, are independently chosen, independently chosen random points in the unit square, then this TSP, this is definitely not the first coordinate. Yet this is concentrated, and the best known bound comes from applying this inequality. Okay, another example is bin packing. Again, a very old and well-studied problem, and there are so many, we can easily just get stuck here, so I'm going to show. This is a lot of very old and extremely well-studied questions this treats. So bin packing, another thing that anybody can understand. So suppose you have n objects, let's say, n computers that each one demands some sort of resource, requires some sort of resource, electricity. But let's say the numbers are between 0 and 1. And you want to satisfy these resources, so the bin packing, B, of these x1 up to xn, is just, you do the following. So you want to find a partition, A1 up to AK, partition of these numbers, of the numbers 1 to n. And now you want to say, you want to partition the indices, let's say xi, I in aj, the total number of requested resource in each of these boxes. Think of A100 is a box. You want to put in A100 these requests, but you want the total, these are positive numbers. You want this to be at most 1. No box has more than 1 demand on it, some bound. And you want the smallest case that which is possible. Okay, so this is a function of the initial numbers, x1 up to xn. I hand you these numbers, and then I tell you, okay, group them up in such a way that in each group, the total amount of the sum is less than 1. You can normalize by a different constant. And you want to do this in such a way that the number of pieces, the number of bins, is as small as possible. Very, very simple question. This is another example of an NP-hard problem. And then you can ask what happens when the xi's are random, according to any measure. So again, so if x1 are independent, then the best bounds can be deduced from that, from the convexity inequality. Okay, and there's many, many more. So these are kind of the vanilla applications. They're non-obvious, and they're all a big deal. But as I said, there are all these other applications which don't involve probability at all. There are theorems in just deterministic mathematics, but somewhere in the guts, this thing is being used. So this is one of many such things. And I want to, when you look at the literature, if you search, there are Talagrand inequalities, and this is an archetypical one. But there's also a Talagrand induction, and the method in which this was proved was also innovative, and I want to say a word about the method before I move on to other topics. Okay, so it's not just the statement, it's also the approach. And actually, of course, the statement itself has something very substantial here, just even coming up with it. Okay, so let me just sketch how you prove it. So the proof is by induction on n. Okay, and I think there are some students here. The fun part about induction is that sometimes you have to strengthen the induction hypothesis. And, so in this particular, so a big part of this is coming up with what is the hypothesis that you want to write. In this particular case, what we're going to prove is that, so you look at e to the a quarter, I think, phi xa, so take e to the power, this number that you are measuring the distance to the set, the expectation of this, according to this product measure mu, squared, is less than 1 over the probability of A. Okay, this will imply, I think it's still up there, right? When the probability of A is at least a half, this is just most to the right-hand side, and you bounded how big the e to the thing that you care about squared is in expectation, so that by Markov's inequality will give you what you need. Okay, so this is what I want to prove by induction. Okay, so we're in this setting, but now let's take n plus 1. I want to place from n to n plus 1. Okay, so now we have a set inside is omega times omega n plus 1. And I'm assuming the induction hypothesis for n. You have to check it for n equals 1. This is a calculus exercise at inequality. But let's assume we did that. This is really an exercise. So if you have a set in a product space, how do you want to apply the induction hypothesis to the product of the first n? Then, right, so there are 2 ways to do it, right? This is A. So you can look at the fibers. So you fix, this is omega n plus 1. This is omega. You take a point here, omega, in omega n plus 1. And then you write A omega is this slice. So it's all the points y in omega, such that if you put right your given omega in the last coordinate, you get an element of A. Okay, so that is, so where this is, right, okay, I should have drawn the slice here, so that would be this and this. That would be A omega, okay? And then in the other, so that's a slice, and the next thing that you can do is a projection. Right, so you can define B to be the projection of A onto omega, which is just the union of A omega. right? So now it's going to be everything. Okay, so that's the obvious two ways to start from a set A and get sets in a lower dimensional object. And what does this convexification of the problem give you? It gives you the following lemma, which it's not even a proof, it's just an observation. So observation is that for every lambda between 0 and 1, if you look at, right, there was this distance to the convex hull. Right, I mean, one dimension higher, so look at x comma omega A, that's less than lambda phi of x A omega plus 1 minus lambda phi of x B plus 1 minus lambda squared. So my letters are big because the room is big, but this is nothing, okay? So this is the kind of thing that when you unravel the notation, it's impossible not to prove it, okay? And those students in the room, there's the opposite of this. I always tell my students, it's also impossible to prove it unless you unravel the notation. So but this is just about unraveling what this says. Right? This was the distance from A to the convex hull of these auxiliary, from 0 to the convex hull of the auxiliary point. So it's witnessed by a point in the convex hull. This is witnessed by another point in the convex hull, but the property of convex hull is that you can take convex combination of these points, and this additional 1 minus lambda squared was precisely because there is one more coordinate, and there was a Euclidean metric. Oh, there's a square. And square. Sorry about that. Okay, so this is really the definition was set up for this. This is what convexity gives you. Okay, but then what did we care about? Right, so we had this over there. Maybe I should start. Right, we had e to the quarter phi x omega a squared. So that's less than e to the phi x a omega squared. There's a quarter. I want to write it like this, to the lambda times e to the quarter phi x b squared to the 1 minus lambda times e to the 1 minus lambda squared over 4. I just exponentiated this inequality. Okay, but we wanted to compute the expectation. So this is a point-wise thing. So notice something interesting here. This was true for every lambda. So I'm allowed to let lambda depend on omega. So what I'm going to do is I'm going to analyze this inequality for a random lambda, which is going to be chosen carefully. Okay? And convexity allows you to choose any lambda, so in particular, we're going to get the best lambda for this. So, right, so if we do expectation just on x, this is the induction hypothesis of what I cared about. So, okay, this. I'm fixing omega for a moment. So fix omega. The last coordinate. This is at most, so we have this e to the 1 minus lambda squared over 4, and then e to the what's written there? Sorry, there is a... Yeah. And then e to the 1/4 phi xb squared to the 1. I hope I copied correctly. This is the thing. This is something that you can see better than me. I copied correctly? Okay, and now this is Helder's inequality, right? Think of Helder with 1 over lambda. So 1 over lambda, so 1 over p plus 1 over q equals 1. And then so I can, this is Helder's inequality. I can put the lambda outside the expectation and make a product of expectation. This, and then put an expectation. Oh, that was good. E. Okay, so this is Cauchy-Schwarz. We saw it in Sarah, but Helder's inequality. Okay? Remember, lambda is still not chosen here, and omega was fixed. But now, this is all happening in the lower dimensional space, so we can imply the induction hypothesis. So what do we get? We get that this is, by induction, e to the 1 minus lambda squared over 4 times what was the induction hypothesis? That was 1 over, p was mu, right, or the product measure. So this is mu of a omega to the lambda, and then we have 1 over mu to the b to the 1 minus lambda. That's the induction hypothesis. I'm applying it for sets in a lower dimensional space. Now, so a omega is complicated, right? So what is the only thing we really know about omega? Is we know that if we take expectation on omega of mu of a omega, we get mu over a. So this is like the nth one, and we get mu is the measure in the n-fold product, and here I'm writing the measure in the n plus 1-fold product. Right, this is just Fubini's theorem. If you take the measure of the slices and you integrate, you get the measure of the thing upstairs. So we really would want something which behaves linearly in mu of a omega in order to, because this was true for every fix, and I want to take expectation here. Okay, so when I stare at this, I would be much happier if there is a mu of a omega which, appearing here, not this behavior. So you force it. So so write it. Let's write it. How would I say it? Let's do it. U of b over mu of a omega. Sorry, mu of. Yeah, okay, so let's do it. Mu of a omega over mu of b to the minus lambda times 1 over mu of b. Okay, but I want to write something linear in mu of a omega, so this is you think about that's the only thing you can do. You write 1 minus this number. Sorry. Look at this thing. times, there was 1 over mu of B, and I put it back. I did something, well, Michel did something, which is just, I multiplied and divided by this term, which is, but here it behaves linearly in the numerator of omega. This is just a rewriting of the same thing. But it turns out that, right, this call this number, I don't know, R. So we have this function e to the minus lambda squared over 4, r to the minus lambda 1 over 2 minus r. It turns out that this function is always bounded by 1. Sorry, it's the minimum of it is always at most 1. So for every omega, there is a lambda depending only on this ratio, which makes this be 1. Okay, so by choosing the lambda correctly, we can make this be at most 1, but now lambda, so apply the Hendel inequality with random exponents. So the claim is that this is just calculus. R to the minus lambda 1 over 2 minus lambda, the minimum of this over r is at most 1. Okay, so this prefactor here can always be chosen to be at most 1 if lambda is chosen correctly as a function of omega. And what remains is now linear, and this you can integrate with respect to omega, and it just becomes the inequality. Okay? So that's how the induction works. And there is many, many more examples of things like this working. They are more complicated and a lot of creativity in just coming up with notions of distance, and again, many applications. I plan to do a few more applications, but I want to change to show some other topics which have nothing to do with this initially. Are there any questions about this? This was just one example of a very, very big body of work, just to show. Are there any questions on this? Okay, so let me just, again, now this is just a random selection of works. I'm choosing ones which are important for various reasons that maybe I can explain in the break. So I have easily 100 papers to choose from. Let me choose 1 or 2 more before the talk ends. So here's a theorem of Talagrand about, it can be viewed as a theorem about dimension reduction or in approximation theory. So it says, so if you have subsets A and B in our N convex, or they don't have to be convex, but there is a notion of Minkowski addition. So you can look at A plus B, which appeared already in Michel's talk. Right, so it's all the sums. It's not an index set anymore. So this is still convex. Okay, so those of you that know, a convex set is a set that when you have 2 points, the interval between them is completely inside, and you can add convex sets. Yeah? Can I do 1 more minute just to say this theorem, or? Yes. 1 minute, it's really the end. Okay. So now, what is the simplest example of a convex set, given that you want 2 points to be joined by an interval? I'm really running a bit late. I'm looking at that clock. Okay, I'm sorry. Okay. Okay, so I'll 1 minute, I'll just say, okay. So the most basic convex set that you can look at is an interval. That's a definition of convexity. So you can look at what is the closure of intervals under this operation. So a zonotope is a sum of intervals. So anything that can be obtained by summing up intervals in many different directions. Example, the hypercube is like that. If you sum the n orthogonal directions, you get a hypercube. Okay, that's a zonotope. A zonoid is the limit of zonotopes in your favorite, let's say, house of metric. So not every convex set can be written as, so this is the closure of this operation of the most basic convex set that exists. So if I give you a zonotope, So if Z is a zonotope, you know that there is a sequence of zonoids which tend to it. That's a definition. All the limits of sums of intervals. But it could be that you need 2 to the 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 n intervals to approximate your set. What Michel proved was that this is not so. If you want to approximate, if I promise you that something is a limit of sums of intervals, and you want to approximate it up to epsilon, then you need only n. You can approximate it using a zonotope that is a sum of only n log n intervals, almost linearly. Removing this log n is a huge open problem and a new idea. So there exists such a decay, such that the distance from zk to z is less than epsilon, let's say in the Hausdorff distance, and zk is a sum of big O, depending on epsilon, n log n intervals. So if I promise you that a convex body is a sum of 2 to the 2 to, is a limit of, at any rate, I can actually get a rate, which is essentially linear in the dimension. And that's a very nice proof in stochastic processes appear there. It's an iteration where in each step, the first step increases the number of intervals, the second step decreases it by, it's a random construction. So you increase it looks like it's going in the wrong direction, but you decrease it by a little bit more, and then you iterate, but so eventually you're going down up to n log n. It's a very, very nice proof, which I'm over time, so I'll stop, and that's just a tiny sample of what he proved.